In this video, I'm going to be talking about fast algorithms for geometric consensuses. This is work with my advisor, Sariel Harpaled, and I'm a PhD student at the University of Illinois. So let's just dive right into the problem. So the problem is going to be the yolk, and the setup is as follows. I have a set of points in some low dimensional space. Let's just think about points in the plane. And I'm going to define L as a median line if it roughly splits the points in half. So formally speaking, L is a median line if at least n over 2 points lie on each side of the closed half space of L. So here I've just drawn an example of such a median line. I'm also going to call a line extremal if it passes through 2 points of the point set, okay? So in particular, what I've drawn above is an extremal median line. We define the extremal yolk as the ball of smallest radius, which intersects all extremal median lines. So in the figure, I can go ahead and draw all such extremal median lines. There's a finite number of them. And we're just looking for the ball of smallest radius, which intersects all of these lines. There is also a problem called the yolk, which is the ball of smallest radius intersecting all median lines. So I've dropped the condition that the lines must be extremal, or that the median lines must pass through 2 points of P. So the yolk and the extremal yolk are two separate problems, and I will stress that later on. The motivation for why we're interested in computing this sort of quantity comes from voting theory. So in particular, it generalizes something known as the polarity point in a two-party preferred system under the proximity model. People who are familiar with that, that's where it comes from. But like I mentioned, the extremal yolk and the yolk are different. Okay, so in fact, for a while it was thought that to compute the yolk, it sufficed to just restrict our attention to computing all extremal median lines and looking for the smallest ball intersecting all of those lines. But this example shown by Stone and Tovey in 92, in fact, shows us that this is not the case. So here I've got an example of 6 points in the plane where the extremal yolk is indeed intersecting all extremal median lines, but the yolk, the large red dashed ball, intersects all median lines and in general is much larger than the radius of the extremal yolk. So in general, these are two different problems, and solving one of the problems does not necessarily immediately provide you a solution to the other. And the focus of this talk today is going to be on the extremal yolk, simply because it's easier to talk about in the techniques we use. So previous work for computing both the yolk and the extremal yolk. The first algorithm was by Tovey in 92, where they get an n to the d+1 squared time algorithm for the yolk. This is improved to n to the 4 time in the plane, but this was the only result that was known to work in higher dimensions. The other exact algorithm that was known was by de Berg et al. In 2018, where they get an n to the 4/3 polylog n time algorithm for the yolk and the extremal yolk in the plane. These are the only exact results that I'm aware of, and so kind of the attention shifted to computing the approximate version of this problem. So namely, you would like to compute a ball which intersects all median lines or all extremal median lines, such that the radius of the ball is at most a 1 plus epsilon factor larger than the radius of the yolk or extremal yolk. So in terms of 1 plus epsilon approximations in the plane, it was shown last year by Gudmundsson and Wong that you can get an n log n to the 7 log 1 over epsilon to the 4 time algorithm for the yolk. Similarly, de Berg et al. Also last year in an unpublished paper showed that you can get an n over epsilon cubed polylog n time algorithm for the extremal yolk. And this was essentially the state of the art for previous work on computing the yolk and the extremal yolk. In the paper coming up at SoCG, we show that in the plane, in fact, you can get an n log n expected time algorithm for the yolk and the extremal yolk. And this is an exact algorithm. So this clearly improves over all previous results. And in fact, our algorithm generalizes to higher dimensions, and we can show that you can compute the yolk and extremal yolk in n to the d-1 log n time, where this notation O of d is hiding factors that depend only on the dimension d. So in today's talk, I'm going to focus on the algorithm that runs in n log n time for computing the extremal yolk. The techniques are also transferred over to the yolk, but there's a little more technicalities there, which I won't go into. So how do we solve the problem of the extremal yolk? What's the first thing we can think of? Well, firstly, we can write a linear program for this problem. So because we're talking about the extremal yolk, we just want to write down all extremal median lines, okay? And these are lines induced by 2 points of the point set. And this gives us n choose 2 implicit constraints, or at most n choose 2 implicit constraints. So just like in the figure I showed earlier in the talk, you have your points and you have your lines, which are the extremal median lines, and the linear program in 2 dimensions, right? You're looking for the smallest point intersecting all of these lines. So you have 3 variables, 2 variables for the center of the disk and 1 variable for the radius. And you'd like to minimize the radius subject to the constraint that the center of the disk, the distance from the center of the disk to each of the lines is at most r. Okay, and so you can solve the linear program in n squared time, right? Any solver that runs linear in the number of constraints will do. But of course, I claimed that we can get an n log n algorithm for this. So how do we get anything faster? And the idea behind this is to exploit the fact that these constraints we have are not just n squared arbitrary constraints. These are constraints with some sort of structure to them, right? The constraints come from the fact that they're induced by 2 points of P. And we're going to exploit that implicit structure in order to get a faster algorithm. So to do so, we're actually going to use a framework for implicit LPs. And this framework was introduced by Chan in 2004, where he was interested in getting an optimal algorithm for computing the center point of a point set. And I'm just going to introduce his framework in the context of our problem. So I'm not stating the framework in its full generality, but just obviously you can find the full generality of the framework in our paper and also in Chan's paper. So here's the setup. We have a set of points P of size n, and I'm going to let LP denote the set of extremal median lines induced by P. What is our goal? Our goal is to compute a solution for LP. And by solution, I mean the ball of smallest radius intersecting all lines in the set LP. Now, the framework Chan introduced assumes we have access to the following 2 subroutines. So suppose that for any subset of points Q of size m, we can perform the following 2 operations in dm time, where d is some polynomially growing function. Firstly, given Q and a candidate ball B, can we test whether B violates any constraints of Q? Okay, so what I'm asking is, does B intersect all extremal median lines induced by the points of P? Or equivalently, is there extremal median line induced by the points of Q such that B does not intersect that line? So this is kind of like a separation oracle in the traditional linear programming sense, except we're separating over these implicit constraints. The second operation, which we assume we can do, is essentially a partitioning step. So given a subset Q, we can construct a constant number of sets Q1 to Qr, such that each set Qi is a constant fraction smaller than Q. And the constraints of Q are partitioned among the constraints of Qis, okay? So all we require is that LQ is equal to the union of LQi for all I. So if we can assume we can do both of these subroutines in d of m time, then Chan showed that we can compute the extremal yolk in O of d of n expected time. Okay, and like I said, I've just stated his framework in our setup, and the framework is actually a little bit more general than this, but this is how it applies to us. So for the rest of the talk, I'm going to focus on how both of these subroutines are implemented, and specifically how we can implement them in n log n time. So let's focus on part A. Given Q and a candidate ball B, does B violate any lines in LQ? So before I go into the subroutine, I'm going to introduce 2 preliminaries. The first preliminary is K levels. So given a set of lines L, the K level is the set of all points lying above or on K lines. Okay, so in this drawing here, I've drawn 5 lines. And the 0 level is just the lower envelope. The 3 level is the set of all points lying above or on 3 lines. And again, I can fill in the rest of the arrangement here with different colors according to the levels of the points in each cell. So it's important to notice here that a single level like the 3 level essentially forms like a chain of these connected components, or a chain of cells in the arrangement. And that will be an important observation when it comes to our algorithm. The other preliminary weight we need is the zone of a surface. So given a set of lines L, a curve gamma, the zone Z gamma L is the set of cells in the arrangement of L which intersects gamma. So in this figure I've drawn below, this dark red curve here is gamma, and I have a bunch of lines. And these blue shaded cells are the cells of the arrangement that are intersected by the red line gamma. It's known that the complexity or the number of cells in the zone is linear, but in fact, we can compute these cells explicitly in n log n expected time. And this has been known since the 90s. So back to the decision problem. Remember, we're given a set of points P, and we're given a candidate ball, and we'd like to decide if the ball intersects all median lines induced by the points of P. So the algorithm is actually going to work in the dual. So using duality, what do we have? On the left, I'm drawing the primal space. On the right, I'm drawing the dual space. So obviously points in the primal go to lines in the dual. A ball in the primal actually corresponds to this region R in the dual. So this region is actually the region enclosed between two branches of a hyperbola. Now, in the primal, we have an extremal median line. So an extremal median line passes through 2 points of P. So in the dual, an extremal median line is going to be a vertex of the arrangement, okay, since duality is instance preserving. Again, in the primal, extremal median lines have at least n over 2 points above it and at least n over 2 points below it. So in the dual, this corresponds to a vertex with at least n over 2 lines above it and at least n over 2 lines below it. And in particular, this is a vertex of the n over 2 level, okay? So if we want to decide if a ball intersects all median lines, this is equivalent to deciding in the dual if all vertices of the n over 2 level lie inside this region R. Equivalently, if we want to decide if there is a median line which does not intersect the ball, then this corresponds to finding a vertex of the n over 2 level which lies outside the region R. So it either lies above the hyperbola or below the hyperbola. And the idea here is that it suffices just to check vertices of the arrangement near the boundary of this region, right? Because the K level kind of forms this chain, right? At some point, the K level has to intersect the boundary of R as it enters R, and then it has to intersect again as it leaves R. So then our task is to decide, is there a vertex of the n over 2 level outside this region R? So in this picture I've drawn here, I'm just focusing on the region below the hyperbola, but you can the same procedure works for deciding if there's a vertex of the n over 2 level above the hyperbola. So what is the algorithm? It's very simple. First, we compute the zone of the boundary of R. Okay, so the boundary of R is this red curve. And again, the zone is the set of cells in the arrangement that intersects the boundary. We look at all of the vertices in the cells of the zone. And essentially the idea will be to walk around the vertices in the zone and compute their level. And if we find at any point this vertex has level n over 2 and it lies outside R, then we're done, right? This shows that the candidate ball is not a valid solution. So walking around essentially can be done in constant time because we start at a vertex, we compute its level, and then we can kind of propagate that information outwards where we use, for a given vertex, we can use the information about its neighbors' levels to get the vertices level. So we essentially do like a graph search type procedure. And this is all can be done in n log n time because we just have to compute the zone, and then we just walk around the vertices of the zone in linear time. So this means going back to our framework for implicit LPs that we can do part A in n log n time. The second part I'm going to focus on now, which is given a set Q, I would like to partition my set into many smaller sets such that the constraints are partitioned among these sets. So let's focus on part B. Remember that the algorithm is working in the dual, so I'm actually going to decompose my problem in the dual. So I have my points P. In the dual, I have my lines P star. And to perform this decomposition step, I'm going to use cuttings. So Recall that an R cutting for a set of lines is a collection of simplices C, which covers the plane, and each simplex intersects at most n over R lines. Okay, and it's been known again since the 90s that cuttings of size R squared can be computed in nr time. So the idea is in the dual, we compute a cutting C of P star, which is our set of lines. And for every simplex in this cutting, we compute the set of lines L delta intersecting delta. And that's it. We've partitioned the constraints among these cells, right? Because each constraint in the dual corresponds to a vertex of the arrangement, and every vertex of the arrangement is going to be in one of these simplices. So we can construct these subproblems delta 1, L delta 1, up L delta 2, L delta 2, and so on. And we can compute this in linear time by computing a cutting where the value of R is a sufficiently large constant. So going back to our framework again, it turns out that we can actually do part B in linear time. So putting both of these ingredients together, you can show that D of M is bounded by M log M, and so the extremal yolk can be computed in N log N expected time. Now, everything I've said here can be generalized to higher dimensions. Cuttings is known in higher dimensions. Zones can be computed in higher dimensions. So in fact, the algorithm just immediately generalizes and you get an algorithm which runs an n to the d minus 1 log n time in R to the d. So of course, there are other applications of Chan's framework and we explore these in the paper itself. So the main one, which is the yolk, which I didn't talk about, is the smallest ball intersecting all median hyperplanes. And the techniques that I've discussed here generalized to the yolk, but there's a little bit of more technicality. The other problem we consider is the egg. And the egg is the smallest ball intersecting all extremal hyperplanes, okay? So in 2 dimensions, the egg is simply the smallest ball intersecting all lines which go through 2 pairs of points. And it turns out that the previous algorithm we have immediately gives you a solution to computing the egg with a small modification. Because if you remember the subproblem we had to solve for the yolk, we wanted to check if there was a vertex outside of our region R of level n over 2. Well, here we don't care about the level. We just want to check if any vertex of the arrangement lies outside R. And so you can do the exact same procedure in n log n time, which means the egg in 2 dimensions can be computed in n log n time. And in higher dimensions, you can compute the egg in n to the d minus 1 log n time. There's 2 other applications which I want to mention before I finish. And so to do this, I need some definitions. So I'm going to define HKP to be the collection of all open half spaces containing more than n minus k points of P. And I define TK as the intersection of all of these half spaces in the collection HKP. So TK is a polytope. So for example, T1 is the intersection of all half spaces containing at least n points of P, which is simply the convex hull of P. And T n over d plus 1 is a polytope which contains the center point of P. Now, if TK is non-empty, then we define the center ball as the largest ball contained inside TK, or equivalently the ball of largest radius. On the other hand, if TK is empty, then we define the TK ball as the smallest ball intersecting all half spaces HKP, okay? And what we show is that the same implicit LP technique of Chan can be used to solve both of these problems in n to the d minus 1 log n time. Now, we also actually get a slightly faster algorithm that depends on k. So what this means is if k is very small, you can do much better than n to the d minus 1 log n. And again, the full details are in the paper. But these are 4 additional applications of Chan's technique we've presented today. And in general, we think there are many more applications of this technique. So that's all I wanted to say today. Thank you for listening.